Delaware Tech, Chemistry 110, Stoichiometry of Gases at STP Conditions. Well, what are STP conditions? STP stands for Standard Temperature and Pressure. We abbreviate it STP because there are actually other conditions that are sometimes called with the long name Standard Temperature and Pressure, so it does become confusing. So use STP when you're referring to this, and STP was, for the entire world before 1982, a temperature of 0 degrees centigrade, which is the same as 273.15 degrees Kelvin, and remember we always use Kelvin in gas law equations, and a pressure of exactly 1 atmosphere, which we know is the same as 760 millimeters of mercury or 760 torr. But in 1982, the rest of the world, except for the US, switched to a metric version of pressure. So instead of 1 atmosphere, they picked a pressure that's just slightly lower than 1 atmosphere, but in a nice round number in a metric unit. And the metric unit is pascals or kilopascals. So the pressure that's now used for the metric system as a standard for STP for the rest of the world is 100,000 Pascal or 100 kilopascal, and we call that a bar. So a bar is close to an atmosphere. It's just a little bit less than 1 atmosphere. It's 0.986923 atmospheres. So the rest of the world uses a slightly different pressure standard than the US does. But so if you're in the U.S., use the old standard, and we'll use the old standard for this class. But if you're anywhere in the rest of the world, they're probably using the metric version of this. Now, at STP, determining the amount of gas that you need for some experiment is very easy to calculate, because it turns out that if we know the temperature and pressure is this set of standard conditions, 1 mole of gas directly translates to 22.4 liters of gas. And it doesn't matter what kind of gas it is. It can be a light gas, like hydrogen gas or helium gas, or an incredibly heavy gas, like a uranium hexafluoride gas. So it doesn't matter what the gas is. 1 mole of gas at STP is 22.4 liters. If you're using the metric system, it's a slightly different pressure. It's a lower pressure, so it's a higher volume. Remember Boyle's law. So if you're in the rest of the world, 1 mole of gas at the rest of the world's STP is 22.7 liters. Now you might wonder, where does this 22.4 liters come from? Well, it turns out if you just use the ideal gas law, PV equals nRT, and you solve for V, so we just divide both sides by P to get V equals nRT over P. Well, now we just plug in those numbers shown at the top, the standard temperature and pressure conditions. 273.15 degrees Kelvin and 1 atmosphere pressure. We know the R value, 0.082057 liter atmosphere per degree mole. And we've got 1 mole of gas. So the idea is here is we're calculating the volume of 1 mole of gas at STP conditions. And when you plug all these numbers in, you get 22.4 liters. So instead of doing this every time, you can just remember, at STP, 22.4 liters. So how do we use this in problems? Well, here are several simplified problems where you've got a certain amount of gas and you're determining the volume, or a certain amount of volume, and you're determining how much gas you have. So in the first problem, at STP, what is the volume in liters of 0.0245 moles of oxygen gas? And remember, if you've got STP and you're dealing with the ideal gas law, we don't care what kind of gas it is. We do care about how many moles it is and how much volume that takes up and what the conditions are. But we know temperature and pressure. We know what they are. And we know that 1 mole is equivalent to 22.4 liters. So we can use that as a conversion factor. So we do what we always do when we're converting things. We start with the thing we have, 0.0245 moles of gas. And then we create a conversion factor. We put moles of oxygen on the bottom because we want to cancel that. And we put liters of oxygen on the top. And we know that 1 mole is equivalent to 22.4 liters. But remember, this is only true at STP. At any other condition, you will have to use the ideal gas law to calculate the volume from the moles. This is the only time you get to use a shortcut. So be careful when you get a problem. If it says STP, you can use the 22.4 liters per mole. But if it's not STP, you cannot use this. You have to go through the long way of calculating it with the ideal gas law. And when we plug this in, we get 0.5488 liters. And since we started with 3 significant digits, and we've got this conversion factor with 3 significant digits, we're going to end with 3 significant digits, 0.549 liters of oxygen gas. Second problem, at STP, what is the volume in liters of 45.7 grams of hydrochloric acid, hydrogen chloride gas? When it's in water, we call it hydrochloric acid. When it's a gas, we call it hydrogen chloride. Now, here we have grams. So remember, you should be used by now to the fact that anytime you see grams, you're probably going to need a molar mass to convert it to moles. And that's what we do first. We need to get the mass first converted to moles of HCl, and we're going to use the molar mass to do that. So obviously, that first arrow will use the molar mass, and we have to calculate the molar mass. And then once we have the moles, we can use our new conversion factor, our STP conversion factor, to turn moles of gas into liters of gas. And remember, this only works for gases, not for solutions. So we determine our molar mass of HCl, of hydrogen chloride gas. It's 36.461 grams per 1 mole. That's a conversion factor. And we can use that to convert grams into moles. We get 1.2534 moles of HCl. Now, we don't round the number yet because we don't want rounding errors. Now we have the number of moles. We use our 22.4 liters per mole conversion factor, and that will give us 28.076 liters, just a little more than 22.4 because we started with just a little more than 1 mole. So that makes total sense. And in the end, we round it to 3 significant figures, 28.1 liters of HCl gas. The last problem on this page, at STP, how many moles of nitrogen gas are present in 1.003 liters of gas? So now we're starting with liters, and we're going to convert that to moles. So you're going to use the same conversion factor, but it's going to be flipped upside down. You want the liters on the bottom. You want the moles on the top shown in blue, and that allows the liters of gas to be canceled with liters of gas, and all you're left with are moles of nitrogen gas, and we get, after we round it, and this should have been rounded, well, if we use the 1.003 liters, you'll see that's 4 significant digits, but the 22.4 liters is really only 3 significant digits. So we round our final answer to 0.0448 moles of nitrogen gas. So, how do we use this in an actual stoichiometry problem? Well, here are 2 typical stoichiometry problems that involve gas. In the first problem, it says, in the reaction at STP, okay, so you know you can use the shortcut. You don't have to use the long way to calculate gases with the ideal gas law. It says O2 plus 2H2 produce 2 water. How many liters of O2, that's a gas, are required to produce 20.3 grams of H2O? So right away you see you're starting with grams, and you have to figure out how are you going to get to the final answer. You're starting with grams of water, but you need to get to liters of oxygen. So what do? Well, we're going to convert grams of water to the only thing we know how to convert grams to, moles of water. And once we know the moles of water, we know the moles of anything else because we have the coefficients of our balanced equation, which we learned when we were studying the first set of stoichiometry problems. So you can turn moles of water into moles of O2 because you get 1 mole of O2 for every you need 1 mole of O2 for every 2 moles of water you produce. And once you have moles of O2, this is at STP, you can use the shortcut to convert moles of O2 to liters of O2. Each arrow is a calculation, and in this case, each arrow can be simply a conversion factor. So we write that out. We can do the first two arrows together, or we can do the whole set of three. I'm separating them so you can see the part of STP separated. But first we convert our 20.3 grams of water using that 1 mole of water per 18.0153 grams of water conversion factor. That's just the molar mass of water inverted. And then we use our balanced equation coefficients to convert 2 moles of water to 1 mole of oxygen, and everything will cancel out except moles of oxygen. So we end up calculating that we have 0.5634 moles of oxygen. Don't round early. And then you're going to multiply that by your STP conversion factor, putting the moles of oxygen on the bottom, the liters of oxygen on the top, and we calculate that we have 12.6 liters of oxygen gas. About half a mole, which is exactly what we started with. The second problem. What mass of NaCl, that's sodium chloride, table salt, in grams is needed to produce 340 milliliters, not liters, milliliters, of HCl gas, hydrogen chloride gas, at STP in the following reaction? So we're given the reaction, we're given all the coefficients, it's already balanced for us. We're given the number of milliliters of a gas. So what do? We want to turn milliliters of HCl gas into grams of NaCl. Well, we know that chemistry doesn't happen in milliliters, and it doesn't happen in grams, and it doesn't happen in liters, it happens in moles. So we have to turn that milliliters of gas into moles somehow, and the best way to do that is first turn it into liters. That's an easy conversion of milliliters to liters. And then we turn our liters of gas, our volume of HCl, into moles of HCl. Once we know moles of HCl, we can determine the moles of any of the other substances in the balanced equation using the balanced equation's coefficients. And once we have the moles of NaCl, we can use its molar mass to convert moles to grams, just like we always do. So I put them all in one place, so each of these 4 arrows is represented by a conversion factor. The first conversion factor allows us to convert 340 mils of HCl to liters of HCl. You notice the mils is on the bottom, the liters is on the top. The second conversion factor, 1 mole over 22.4 liters, is our STP conversion, which we can only use at STP. And that allows us to convert our liters of HCl. And you can always tell what you're on by just looking at the numerator of each conversion factor. That's what you converted it to. So after the first conversion factor, we've turned it into liters of HCl. After the second one, we've turned it into moles of HCl. And now we need to turn moles of HCl into moles of a different substance, NaCl. Well, it turns out there are 2 moles of NaCl for every 2 moles of HCl. So that's an easy conversion. It doesn't change anything. And then once we have moles of NaCl, that's the top of the third conversion factor. Now it's an easy conversion using the molar mass of NaCl, and you'll have to calculate that yourself. And that is 58.443 grams per mole. So we put the moles of NaCl on the bottom, the 58.443 grams of NaCl on the top. We multiply it out, and we round it to 3 significant figures because that's what 340 is, it's what 22.4 is, and therefore our final answer is 0.887 grams of NaCl. And we'll stop here.